So, okay. So, you have to find a way to get some more information from bright field microscopy images, and there. So we have to figure out is it possible to predict fluorescence images from bright field cell images? And I think the deep learning model is an approach with a conditional generative adversarial network, so CGAN for short. And why this might work? So the CGAN learns a mapping from input image A to the output image B. So basically, this should be your output. This is the ground truth. And um, there are two neural networks in CGAN, a generator and a discriminator. So the generator tries to fool discriminator into seeing the fake, the fake output is real. And the discriminator tries to tell between the real and fake. So it is possible to synthesizing photos from labeled maps. For example, this is the best example I can find, actually, and even transforming sketches into photos. Since both bright field and fluorescence images capture the same thing, basically the same cells and structures, the statistical correlation exists. Now let's talk about my data set. So the original images are kind of big, is 2048 pixels times 2048 pixels. And I have to downscale them to 256 to 20. So basically, I have to reduce the resolution by a lot uh, due to my hardware constraints, you know. And so basically, the images here are my image set. So the left here are the bright field images, and right here are the fluorescence images, and they are both in grayscale. So the total amount of image set in my data set is 1986. That's not a lot, to be honest, but that's the data set I can find. Let's
Can
go
I
over.
can I ask a quick question? You
Uh,
said you reduced the resolution from 2048 to 256.
uh-huh.
Was that truly the resolution was reduced, or was the field of view reduced?
It's the resolution because in my Python script, it reduces the resolution.
And you chose to reduce the resolution versus just a smaller field of view because why?
Um, um, because I think like either will work, but I'd like to preserve like more cells to show maybe that will bring a better result. But yeah, I think either will work. Yeah.
Okay.
Okay. So let's go over some basic concepts. The first is convolution. So basically, it extracts features like shapes, outlines while reducing the noise. This is a basic illustration of how convolution works. So basically, for this pixel, um, we use a filter, like for example, 1 times 1.2, and added all of this together, we get a number. So this is a convolution, the result of convolution. And a rectified linear unit, or ReLU, uh, it lets the network learn relationships like curves, textures, edges, and other nonlinear structures. So it often applies after the convolution. So both convolution and ReLU are used to extract the features. And there's also max pooling. So it takes a region like 2.2 and keeps only the maximum value. So this is a way to reduce the spatial size. It's also called downsampling and keep most important features here. Okay, now let's talk about the generator. So the generator is basically a modified UNet. First, what is UNet? So it generates real-looking images in the CGAN. And in the UNet, there is a part called encoder, and there's a part called decoder. So basically, this contracting path is encoder, and this is decoder. The encoder compresses the input. For example, input is 572 by 772, and into abstract features via convolution. So these are the convolution. This blue arrows are convolution, and max pooling. Sorry. So it learns what is in the image by generating feature maps. So this number here are the number of feature maps in each level of this convolution at max pooling. And these feature maps are basically like the image that shows where and how strongly a certain pattern appears in the input image. And the decoder reconstructs a new image from those features by reverse process encoder. So basically, the decoder is just a reverse process of the decoder. Oh, well, no. The decoder is the reverse process of the encoder. I'm sorry. Okay. And the resolution of image decreased several times. As you can see here, this is 570, 568. This is like 280. This is like 140, 68, 64, 32. So the resolution of image decreases several times in the contracting path. Does that mean the final detail of the image is not? Actually, the detail is not losing here because of these gray arrows. They are called like the copy and crop. It connects encoder features to decoder layers here at the same resolution. It helps decoder localize objects accurately and prevent loss of fine detail during the downsampling. So the last wording about generator is it learns when I see this kind of pattern, I should paint this kind of output. Okay. So this is the generator used in this project. So basically, it's from like 256 to 256 to 4x4 is can I like make it larger? Yeah, with 1024 feature maps. And the strided convolutions are hidden in these sequential blocks. Um, so the strided convolution is basically just like I mentioned earlier. So this is convolution. We go by this pixel and that pixel. Strided convolution is like we do one pixel and skip several other pixels and do the next pixel. So this is also a way to reduce the resolution of the image. Okay. And so the input is the bright field image and the output is the generated fluorescence image. And the generated output goes to the discriminator. Uh, how many how much time did I pass?
That was 9 minutes, so you have about 11 more minutes.
Yeah, I think that's enough. Okay. So this is my discriminator. So basically it takes the fluorescence image and the bright field image. This is so input here is the bright field image. The target image is the fluorescence image, and they combine all layers together. So basically by this concatenate step. So similar to UNet, it uses strided convolution to reduce the resolution and extract the features. And in some steps, zero padding is also involved. So basically, it adds edges of zeros around the border of the input. For example, if this is an image, we add a round of zero. And it prevents the image shrinking because if we don't add that round of zero, uh, some uh, some pixels around the edge might be unable for convolution. The output here is a 30 by 30 by 1 matrix with numbers between 0 and 1. So it gives a realism score at like each pixel of the output. So every of these 900 numbers will be used to calculate the sigmoid cross entropy. We will talk about it next slide. So here's another round of concepts. I guess they are not no longer basic concepts. They are very confusing concepts. So first, what is mean absolute error or MAE? It measures how different two images are pixel by pixel. This is the function. And the sigmoid cross entropy. It measures the difference between the model's prediction and the correct answer. This leads to the adversarial loss. So this is a loss function, and this is the function for the sigmoid cross entropy loss. And there's also a parameter called lambda. So this is the weighting factor used to balance two losses in the generator. For example, the total loss is defined by this adversarial loss and lambda times MAE. The high lambda means better to better pixel accuracy, but maybe in the sacrifice of the realism. And the low lambda means the realism is more important here. Um, and apply gradients. This is the most confusing concepts. Actually, I'm still cannot totally understand this. So this step compute error and update the filters to improve the result. The filters is just in case you are wondering, the filter is just this thing. Sometimes I also call it kernel, but it's just the same thing. You can understand. And so how do we train the generator? So the generated image is used to calculate the MAE from the real image and will be put into the discriminator. The discriminator will produce realism scores while we pretend all generated images are real. So when the realism score is closer to 1, the adversarial loss from the sigmoid cross entropy is little. So that combines with the lambda times MAE, as I mentioned earlier, we get the total loss. We can use this data to apply the gradients. And the goal here is to fool the discriminator. So the discriminator think all of your generated stuffs are real. So we have to keep the total loss real, low. So, okay. How are we training the discriminator? So discriminator takes a bright field image and corresponding fluorescence image, either the real one or the generated one. If the fluorescence image is the ground truth, 1 will be used to calculate the adversarial loss. And if the fluorescence image is generated, 0 will be used to calculate the loss. The losses are added together to apply the gradients and feedback to the discriminator. The goal here is to push the real predictions towards 1 and the fake predictions towards 0. And before I show you the training result, so this is basically my training setup. I'm using my own gaming laptop with Java 3.0, and I'm running TensorFlow 2.0 because this is the last version that has the GPU support on Windows. I tried to install Linux on Windows, but I couldn't figure out how. So I can only use this a little bit like old TensorFlow version. I think this was released like back in 2023, so it's not that old, I think. Yeah, and so TensorFlow is a framework to construct all of this kind of neural networks. And it also includes an important function called TensorBoard. So it tracks the training progress, the loss versus minutes. So here in this image, this is the time in minutes. After each 100 minutes, it goes back to the 0. So that's why you see this like horizontal lines. And the vertical axis is Gen L1 loss. So basically, in the code, this is MAE. And here are some results. I'm not sure if you guys can see it clearly, but you guys might have to like increase increase the brightness of your screen because there are some they are kind of dark here. So ground truth, this is the ground truth, this is the predicted image. And I'm gonna be honest, these are the best ones. Yeah, they are worst ones. Okay. So the MAE might be increasing over time, not decreasing. So that's because uh, you guys can see this, right? So the
Huh?
MAE actually might increase over time. Yeah, it's not always decreasing. That's because the generator and the discriminator, they don't have the same training speed. So to make this training more efficient, we have to tune the training plan. So basically the batch size, the lambda, or maybe even the data set. And there seems to be a limit where the MAE cannot be lower. And MAE cannot be zero, that's for sure. Because after all, this is the predicted image, not the ground truth. And
Is it possible for you to select one of those or three of those images and change the contrast so that we can see something? Because to be perfectly honest, the first column is mid-gray, the second column is dark gray, and the third
um,
column is slightly brighter gray, but there's no features in the pictures on my screen. So I can't really.
there are like some features I'd say you can see, for example, here. But I have to like maybe put these images into like Photoshop, GIMP, or some
Yeah. Well,
image
if you
processing
click on it
algorithms.
with your mouse, click on that picture with your mouse. Is it an individual picture? Okay, so you got three
Um,
there. There should be a way to change the contrast. Uh,
uh, this is the output in my Python notebook. So I just take the screenshot of them.
I see. I see.
Yeah, but if you really want, I can show you the Python the complete code. Yeah, actually I can do that. But
Well, I don't care to see the code so much as see images that have features in them. Because I don't really see anything in these pictures. Oh, I see there's some very dim things in the second row there. Okay. And so what's the difference between all these rows and everything? What is this?
so this is the bright field image, this is the ground truth, and this is the predicted image.
Oh, and these are just different examples as we go from top to bottom. Is that what you're showing?
Yeah, these are the different examples. These are
I
the
see.
best result I can find, to be honest.
I see.
Yeah, let's to show the training effect.
Ah.
Okay.
And it says here lambda is 1,000. That's a big number.
Yep.
What is the range that lambda can achieve? Like if I set it to one, uh, what is the balance between the two uh,
Um,
numbers?
I chose 1000 because I tried other numbers, but 1000 seems to be the one with the lowest MAE I can get. I mean, in a reasonable time. For
And so when you
example,
set it to 1,000, does that basically eliminate one error testing part and put everything into the term that has the lambda 1,000?
um, well, that's a good question actually. And but
Like if I go to that
um,
formula and I look at my total loss, and you have adversarial loss and you have lambda MAE, and I set lambda to 1,000. I don't know the range of adversarial loss and MAE. Is it 0 to 1 or is it?
MAE mean so
So we don't basically know what 1,000 means in this formula in terms of balancing the MAE and adversarial loss.
yeah, to be honest, I read some papers and other people's article. This all they sometimes start with like 100.
Uh-huh.
Yeah, but I tried 100, but the result is like worse compared to 1000.
I
So
see.
yeah, I use 1000 at last.
So there wasn't really any tuning of lambda as such. You just a big number seemed to work. better?
Um, so maybe I should try more lambda values to be honest, but this is the best one I can find.
Okay, it seems oddly specific that it came out to 1,000. But anyway, I don't know
Mhm.
what the dependence of the performance versus lambda and anything like that. We'd have to know, right? So,
Yeah.
okay, all right.
Okay. So some summary and reflections. So the project explores the possibility of translating bright field images into fluorescence images. And this might be a helpful technique to image living cells. And the concepts involved in artificial neural networks are investigated, bringing an introductory level understanding of CGAN. And a CGAN was built, including a generator and discriminator. The training result can be observed via a quantitative way. So basically, we can track the L1 loss here. And the detailed math behind these concepts are not thoroughly understood, especially for the applying gradient part. Actually, it took me some time to even understand what even is a gradient. And maybe I can try this network on other image translations, for example, DLC to fluorescence, or maybe like from fluorescence to bright field, like translating back. I might also use larger images for training, start with 512 by 512. And here are my references, and that's all. Yeah.
Okay, thanks. So the one big question obviously is why do you pursue the hypothesis that you can generate a fluorescence image from a bright field image? What physical underpinnings of bright field microscopy directly map to fluorescence? So that you
Um,
know that if I have the bright field, I know kind of how the fluorescence will look. There's enough features in here that tell me what the fluorescence is probably going to look like.
so as I said in this page, they are essentially the same structure. So there have to be some statistical links. And yeah, I just read about this idea and I feel like because of statistical links exist, this might work. Yeah.
Okay.
Mhm.
I
Any other questions?
Does anyone from the class have a question for
I have a
Jason?
Okay.
question.
Hello, Cassie.
Um,
Cassie?
I thought your results looked really good. Like we're doing again and we're struggling a lot. So I'm impressed that it looked like to me your ground truth looked exactly like your the output. Um, so I don't know. I thought I'm just curious, like if you didn't change the lambda and like the weights in that way. Like I'm just curious what you changed in order to get a good result, basically.
Yeah, so lambda is of course changed a lot here. But I also changed the depth of the generator. So the depth here, so this is 4 by 4. It can even be 2 by 2 or 8 by 8. That will also change the result. And well, to be honest, these are the best result I can get
Hmm,
to show here. They are worst results, so don't worry if you are doing the same thing. Okay. Yeah.
cool.
Okay, great. Any other questions from the class? All right then. Um, let's see where we are. Um, so Diana and Benjia, you want to, oh, I guess you're next. Sorry, Casey and Bryce. My bad.
Yeah, we can go.
Can you guys see the screen?
Yes, I can see it now.
Okay. Can we start whenever?
Sure.
Okay. So hi. This is the project done by my partner Bryce and I, and our project will discuss deep learning-based dual phase segmentation of the left atrium and left ventricle across cardiac phases. So just to give a quick overview of what cardiac segmentation is, it is defined as a process of identifying and outlining specific anatomical structures of the heart. It is essential for assessing structural and functional cardiac health, and it can produce measurements as its outputs, such as chamber volumes and ejection fraction. It can help with a number of conditions, cardiac conditions, such as heart failure, myocardial wall thickness, and ejection fraction. So there is manual segmentation that has been done in the past before, but more recently with the revolution of AI and deep learning models, there's the introduction of unit, as mentioned in the previous presentation. It can be defined as a convolutional neural network or a CNN, and it automatically segments 3D structures, and it can provide accurate, reproducible, and fast annotations to support diagnostics and surgical planning. Um, so the input for this model, for these models, are 3D image volumes, and for the outputs, they output 3D segmentation masks. So what are segmentation masks? So if you look on the image to the left, this is an example uh, picture of an elephant. So let's say you only want the output of the segmentation mask output to only feature the elephant. So so what masks do, there are different type of masks. There are binary masks, which is an example of the elephant here, where you want where zeros can where the model applies zeros for background voxels and ones for whatever the region of interest is. So in this case, it would be the elephant. So the the model would apply ones and color the region of the elephant green, and that would be the mask. And the output or the segmented image would be the mask and the original image laid on top of one another. So you can see that the mask clearly outlines the elephant and the outputted segmented image. So to go more into our motivation slash problem, so as previously mentioned, manual segmentation has limitations. There's significant human labor as each scan can take up to 30 minutes. And there's also variability into cardiac assessments where different cardiologists can interpret these images differently, which can lead to um, conflicting results. So automation is needed to improve the scalability and standardization. Chamber compliance and systolic performance need observations of end diastole and end systole phases. So with our project, we aim to reduce time and variability between observers, enable segmentation of both left atrium and left ventricle, use end diastole and end systole images to improve diagnostic accuracy, and calculate the stroke volume and ejection fraction. So as I mentioned, there has been advances in 3D deep learning models using UNet. But we found, based on the current state of the art, that current models are limited to either the left ventricle slash the left atrium, or conversely, one of end diastole or end systole. Um, so more to get into the problem or the clinical relevance of how our project would fit into the to I guess the medical imaging field, it will be able to accurately um, quantify ejection fraction and stroke volume estimation. It can also help with diagnosis and risk stratification for heart failure and atrial fibrillation. It can also reduce the manual workload for radiologists and cardiologists as they can just feed it into the deep learning model and gain outputs relatively quickly compared to manual segmentation. As I mentioned before, another big problem was the variability between the cardiologists and their assessments. So this would help standardize measurements across not only cardiologists working in the same lab, but also across different institutions and observers across multiple locations. It can also help facilitate early detection of cardiac remodeling and dysfunction, and it could also hopefully seamlessly integrate itself into clinical workflows that already exist, such as PACS, 3D Slicer, and ITK Snap. So our objective, or I guess our problems, statement is we aim to develop a deep learning pipeline that employs dual phase segmentation of the left ventricle and left atrium from 3D cardiac images at two key cardiac phases, which is the end diastole and end systole. So now we'll talk more about our data set. So our data set, we're from 40 subjects, each with 3D volumetric images at end diastole and end systole phases, which results in a total of 80 images. So as we talked before, each image came with their individual mass for both the left ventricle and the left atrium, and no left ventricle and no left atrium labeling or the mass overlapped. Ground truth labels were done to show exactly where the left ventricle and left atrium were located. And then this is the images, uh, I guess, and cyan color is labeling the left ventricle, and the blue with the more darker blue color is where the left atrium um, would be shown over time in these scans. Yeah. So next, you can go into more of our pre-processing. So before we fed the data into our model, we wanted to make sure that it was very consistent and very there were no outliers, and we wanted to make our model as precise as possible. So during inference, you feed full images with air too, just as real world images account have not only have the cardiac system, but also have background artifacts such as air or other things. So we tried to replicate this as accurately as possible, and we manually removed files with depths unequal to 256. So as we see on the graph here, um, a large majority of our images had an image depth exactly to 256, but we found that some images had there were outlier images that had depths such as maybe like 120 or like 410 or like 650. So we decided to remove those images as we wanted to make our data set as consistent as possible. And we also chose to resize our images from its original size of 512 512 by 256 to 128 by 128 by 64 to to make the training segments of our model more efficient. Uh, in addition, there's additional pre-processing as well. So uh,
Can
we
I
normalize,
ask a quick question about that? Can you
yeah.
define what depth is? I'm not sure I understand.
Depth is the z-axis of our images.
Oh, number of slices?
Yes.
I see. Okay. And so you basically unified everything such that it went into this 128, 128, 64 over the whole original field of view?
Yeah.
Okay. So you didn't isolate the heart, you just did the whole thing.
Yeah. Yeah.
Okay.
Uh,
Were the Okay, and so the 128 by 128 by 64, the actual spatial dimensions of those voxels varied from person to person.
yeah.
If they were in millimeters, they would vary because it's
Yes.
okay. All right,
Yes.
thank you.
So also we decided to normalize the intensities as we found that a lot of the current models normalize them as well as we looked through papers and such. So we decided to use min-max values. There are other papers that normalize using z-score values, but we found that min-max values were better for our model, and we decided to put these at 2,000 Hounsfield units and at a minimum of negative 2,000 Hounsfield units. And we did this in order to account for scanner variations across institutions and as well as across different images as well. And for specific augmentation, we chose to account for breathing corrections and movement during the CT scans. So we found that rotations were the best augmentation in order to replicate this. So in order to try and show the movement or breathing corrections during these scans, we decided to incorporate random rotations of plus or minus 5 degrees in order to show this.
About
And
what
also
axis are you rotating? I'm sorry.
We're rotating around the all three axes, so X, Y, and Z.
Oh, I
Oh,
see.
we're just doing along the XY plane. So along the axis.
I see. So you have an XY image, Z is perpendicular to us, and you rotate this way.
Yeah.
Yeah.
Okay.
And he also did some class balancing to add weights to address tissue volume imbalances from image to image. Um, so yeah, so that was our pre-processing, and now Bryce will get into the nitty-gritty of our training and results.
All right. Um, hi. So I'll talk about the model architecture. So this is the unit that we're using. So it's pretty lightweight. Also, like, I think Jason talked about it a little. And so we're employed a 3D unit. So I think he's using the 2D one. So to change it to 3D, we're basically um from the just make the functions inside the inside the 2D unit, just make it 3D, and that way we'll preserve the through plane anatomical continuity. And the architecture uses a classic encoder-decoder structure with five downsampling layers, and this increased the filters from 64 to 512, and this capturing the features at multiple scales. And we use five upsampling layers, include dropout for regularization and reconstruct the full resolution segmentation. A key feature of our model is the incorporation of dual dual phase ED and ES volumes. And I want to clarify that we actually trained separate models for different phase combinations data to compare their effectiveness, and that's our method to incorporate this. And and we use skip connections for spatial detail preservation and um and the outputs is multi-class, so background, left atrium, and left ventricle.
Can I ask a quick question? When you say you have mul you had two networks, one for end diastole and one for end systole?
Oh, we have actually three. So like end diastole and systole, and then we pulling all the data together and separate them 50-50, and then train another
Oh,
network
so you
to
have
see like the
one network that did end diastole, one that did end systole, and one that worked on shuffled data that has
yeah.
both phases. Okay.
Um so to our training procedure. Our training procedure was designed to handle the computational constraints. So we resize it, and then we address the class imbalance, and we use 50-50 ratio to make the three models consistent. And then we have tw 20 epochs and using batch size 2. And for the loss function, we use the TensorFlow default sparse categorical cross entropy loss. And and this is because shown in the figure below, you can see the segmentation inside the whole thing is pretty small. So I think this loss will entail that. And the and we use dual phase versus single phase. And here's the dual phase results. So this approach we trained on both the endoscopy and systole data combined, and the training curve shows excellent performance. We achieved rapid convergence with validation accuracy reaching approximately the 97% and maintaining stability throughout the training. And the loss curves showed the model learned effectively without overfitting. With training and validation loss both decreasing steadily. And I think what's particularly interesting is how the model quickly converged. So on like epoch 2 to 3, we're already achieving some of the very good results. Um,
How do you explain the training accurate or the validation accuracy being so high on your first epic?
Um, okay, so I th yesterday I think about it because I think it's weird. I think my explanation is like so the data looks re like fairly alike. So even if you're just seeing like a couple training data, I think that's enough. I don't know, like I think I still need to like work on it, but that's my hypothesis is like those like 3D images, it look basically like structurally alike, and then I think that kind of explains why the accurate and I'll show in the single phase the accuracy is pretty high as well. So I think that might be one reason why. But
It
The
does
loss
too.
value also looks pretty low if you like it's not starting from a very high loss and then
yeah, exactly.
like trading for a loss thing.
I see. So that loss that is very low to begin with, so it just
Yeah.
maps to that accuracy. So accuracy is not a sort of sensitive marker.
Yeah, I think it's maybe also like changing the loss function may change like the how the model learns
So
as well.
I see. But does this have anything to do with the fact that you're using the whole volume and a much smaller heart in that whole volume? So calling everything zero, your accuracy is going to be pretty high. Right.
Oh, I think I think we're capturing the whole image
Yeah.
if
But this goes back to that
yeah.
balance, right? You've got a small heart inside a big volume, relatively speaking. So even if your network just said none of this is hard, the accuracy would still be pretty good because it would get so many right.
That's true, I think. Hmm. Yeah, I think that's
How
true.
big is your data set?
It's only like 80 data,
Yeah, I think
80
it might be just
plus.
memorizing everything.
Oh, okay.
Yeah. All right. Going to the next. So this is just a visualization of our predicted mask, and I think it did a pretty good job. At like this specific one. Not like I just looked at a couple and they did pretty good. Um, so you can
What,
see.
I'm sorry, what am I supposed to compare? Can you take your mouse and tell me what I should be comparing here?
So the above is like the true mask.
Yeah,
So basically, we're taking the 26 slice through 43, so like 18 slices,
okay,
and we want to see the segmentation in each slice. So
okay,
comparing like up and down,
yeah. Okay, so
you
I
can.
see it is very good in the middle row and the bottom row. There's a bit of problem in the middle row, I guess, on 33 is a little bit different. And 34 is quite different, and 35.
Yeah.
Yeah, okay. And then 26 seems to be, it's gone crazy,
Okay.
right?
Um. So that's some like minor visualization issue or like plotting issue that I have. So I forgot to like say like, okay, so label one is one color and label two is one color. So when the picture has only like one label, so for example, like left ventricle, so it just assign one,
Oh,
like the
oh, I see.
default color.
I
So
see. It's a
that,
bug when you only have one label. Okay. All
yeah,
right.
yeah.
Yeah, got it.
So I think it kind of captured the structure pretty well.
Yeah, yeah, it's not bad. I mean,
Yeah, also I think the the imbalance should is also a big issue, I think. Because I think I tried like different weights. I try so instead of 1 2 2, I try 1 3 3, and then the accuracy is pretty high, but when I look at the visualization, I didn't I think they're all like zero. So that might explain why,
So
like, if you,
these field of views that you're displaying here, that's the original field of view in the image that you were using?
yeah,
Okay. So the heart is a significant part of that field of view, right? I mean, it's still the ventricle is still probably a, I don't know, a tenth or something, but it's not 1% or something.
yeah, it's not, it's the whole image. Okay.
And
And here's the
go,
res
go ahead.
yeah, here's results, just trained on the and diastole data, and it just follows the same trend, and accuracy is really, really high, just from the first epoch. Um,
Mhm.
and still like the loss is like low in the beginning. Um, I think we can just jump to the visualization. So here you can see they also did a pretty good job. So this is like tested on the end systole data. So we trained on the end diastole data, and then we validate them in systole data, and it did a pretty good job at
Mhm.
identifying everything. Yeah. And the same trained on the and systole data, and visualization is pretty good. So to our discussion. So the key finding to me is surprising is that even though we train on only single phase, it can generalize across cardiac phases. And since we're only use this very lightweight 3D unit model and it learns the anatomy features fairly quickly, it 20 we only take like 2 minutes, and it is really high accuracy. Maybe suggest like effective pre-processing, but also suggest some like error about the class imbalance. And clinical implication, this could potentially be used for automated cardiac assessment and reduce the radiologist workload and standardize the measurements across institutions. Here are some limitations. So first, the data set size is pretty low. We only have 40 patients versus thousands needed for clinical validation. And also, this I forgot to ask about the pathology diversity, but I assume it's not that diverse. So, um, need validation across cardiovascular disease spectrum. And we also only did like rotation across the axis, and it's limited to 5 degrees. So rear-motion can be more severe and more like complicated. So, and also we can evaluate more weights, and future iterations could implement like automated hyperparameter search.
I'm sorry, what do the weights correspond to? I missed that. Must have.
Oh, so the weights, so we basically assign, um, so basically 1 to 2 is one. So the first element is background, and then second, third is left atrium and left ventricle.
Uh-huh.
So basically, I assign like more weights to the atrium and left ventricle to kind of mitigate the imbalance of the
I see.
classes.
Got it.
Yeah.
Okay, thank you.
And but surprisingly, 1 to 2 works better than, so 1 to 2 is what I've shown, but 1 through 3 just totally like zero, like background, but accuracy is pretty high as well. So that makes me wonder why.
I'm sorry, 133 did what? Different than 122?
The 1 through 3, when you visualize the data, the segmentation, it just assign everything to background, but the
Oh,
accuracy is still pretty high.
I see. Okay.
So yeah, so maybe that's a problem.
Yeah.
But surprisingly, 1 to 2 works pretty well. So
Cool.
maybe we're just lucky. Yeah. All right. So conclusion, um, and future work. future work, we could use different augmentation, like I said, because the movement is pretty complicated. To use like rotation across different axes and then combining like translation, shearing, and like them together to monitor it. And then we could include other parts of the heart and we could integrate with workflows for easier access.
Cool.
That's our references.
All right.
Yeah.
It's hard to know unless you had people that actually do have that disease where your body is reflected through the midline. Like some people have mirror image bodies, uh, but reflections.
Yeah.
Otherwise, I'm not sure unless somebody fed the data in the wrong way. But okay, that's kind of supports, our observations that a lot of these networks can get trained very quickly and on very few examples if you have data from the same place. Like if it's from the same scanner and the same protocol, we've also found that you can train a network in like tens to dozens of images, and it'll do pretty darn well on the 10,000 images that are left out. So which is good, right? So this sort of confirms that hypothesis to a certain extent. Cool. Any
Yeah.
questions from the class? And and if I understood correctly, you said your network trained up in 2 minutes?
Yeah. We only use like 20 repetition.
Wow.
So yeah, it's just amazing how this very lightweight model
Yeah.
can, yeah, I don't know, just AI, I guess.
Yeah, that's amazing. Um, okay, great, thanks. I think Marco, you have a time constraint, right? Do you want to go next?
Yeah, definitely.
Yeah. If we can do that, because I think Marco has to travel after today, so let's make sure we get him in here and then we'll go back to Diana and Benji.
Can you all see my screen?
Yes, sir, I can see it.
Okay, great. Let me start my timer real quick. All right, hi everyone. Today I'll be presenting my project, which I pitched 3 weeks ago. I titled it Incorporating Left Atrial Global Metrics to Left Ventricular Strain to Predict Response to Cardiac Resynchronization Therapy, or CRT. Okay, quick 30-second overview of the clinical need area. CRT is a well-established treatment for patients with heart failure, but approximately 30% of patients do not respond to the therapy. Although it's not open heart surgery, it's still invasive under anesthesia and should be prevented if not necessary. Therefore, it would be advantageous if we can use tools to better inform patient response. While echo and MRI have been used to improve lead placement, their limited reproducibility and their compatibility have prevented adoption. So here we'll explore the use of 4D-CT to better predict response to CRT. So this is a slide I presented last time. It's going through the study of Ashish and Dr. McVeigh back in 2023. To summarize just real quick, 82 patients were retrospectively analyzed. They received the 4D-CT scans before and 6 months after CRT. The team had manually segmented the left ventricle across all the time points for each of the patients, and using this mask, they could then calculate where's my mouse here? The global and regional strain metrics and append them to each patient's clinical features. By moving to the last box, they then trained a support vector machine to generate an overall score per patient, and by assigning a threshold value, patients above this value were predicted to respond to the CRT, and below this value, they would not respond. The overall conclusion was that both the global and regional strain metrics of the left ventricle could be used to predict CRT response. And with this model, they achieved AUC or area under the curve of 87%. I added the slightest feedback from Dr. McVeigh last time, but ultimately, why do we care about the left atrium? So in left-sided heart failure, the left ventricle struggles to pump blood, which can cause pressure to back up into the left atrium, and over time, this can lead to left atrial enlargement and potential damage. It can go through structural changes like hypertrophy, lose its ability to act as an effective pump, and even contribute to mitral valve issues. So given all that, we're asking, can these measurable changes in LA function, or specifically LA strain, help us better predict who will respond to CRT? This is the proposed plan slide I presented last time, and in the flowchart, I highlighted the adaptations to Ashish's methodology in blue, while the gray boxes are what stayed the same. And this is what I was able to get done. So the checks are what I was able to get done, while the crossouts I either didn't get to or we decided to move in another direction. So to start off, I used the same 82 patients with pre and post TRT 40 CT scans. We didn't get the chance to test on more patients, but this could be a potential next step. Then I was able to use a segmentation model to segment 9 chambers of the heart, of the left heart, for all patients across all time points. So this includes the left ventricle and the left atrium. And moving to the middle, for the metrics, after computing and analyzing with left atrium global values, the results looked pretty decent. So I didn't feel the need to incorporate the regional metrics. And then lastly, for the models, I was able to replicate Ashish's findings with the SVM, as well as input the features table into 2 additional supervised learning techniques, including the random forest and a logic gradient boosted tree, which is pretty similar to the XG boost, but that's the only one that was available on MATLAB. And again, the results look pretty good with these models, so I didn't go forward with the deep learning with the CNN RNN hybrid model. And before I go over the AUCs, I'll explain my methodology in a bit more detail, just in case y'all have any questions. But my first step was segmenting using the segmentation model. So with the help of one of my lab mates, Amanda Crane, we were able to adapt this heart segmentation model that was developed by Lauren Severance, one of Dr. McVeigh's former PhD students. I used it to segment 9 chambers of the left heart across all time points pre and post CRT for all 82 patients. So that's a lot of data. First, I was running CPU and it took almost a week to run, but then I did a GPU and it was less than a day. So that was pretty cool. In the visuals, the red corresponds to the left ventricle and the green corresponds to the left atrium. So you can see here the 3D rendering of one of the time points. Again, the red, the largest, is the left ventricle, and the green is the left atrium. And yeah, pretty good results. And first, I just want to review the features table and what it is. So these are the contents of the original features table that Ashish used back in 2023. The table includes clinical features as well as left ventricle, regional, and global metrics. But what's important is that these strain values were calculated from segmentations that were drawn manually. So that differs from my model because in my updated features table, we have the clinical features as well as the left ventricle, global, and regional strain metrics, but these metrics were calculated from the segmentations that were automated, like I just said, from Lauren's model. So we have both manually as well as automatically derived global strain metrics for the left ventricle. The major change is the addition of the left atrium global strain metrics, obviously. These included the maximum and minimum volumes across the time series, almost as proxies for end diastolic volume and end diastolic volume for the left ventricle. I also included the left atrium ejection fraction from these values and then the sphericity. So to calculate the sphericity, I divided the actual volume of the left atrium by its theoretical volume had it been a perfect sphere, which is calculated as pi over 6 times its longest axis cubed. Okay, so some sanity checks just to make sure that our segmentation worked. The segmentation was actually my biggest bottleneck. So there were many, many different redos because there were many repos and I had a bunch of compatibility issues, but eventually we got there. So pretty happy that we got there. So instead of looking at every patient's before and after scan for all 20 time points, Dr. McVeigh gave me the idea to plot everything and inspect for any outliers. So here I did just that. Here, I'm looking at the left ventricle's ejection fraction from the manually versus automatically derived segmentations. The graph you're seeing is plotting all of the patient IDs on the x-axis and the ejection fraction percentage on the y-axis. For each patient, we're only plotting the ejection fractions from the pre-scan, from the pre-CRT scan, since that's the only manually acquired segmentation that we have. The X corresponds to the manual acquisition and the filled in circle to the automatic. If the difference between the two is larger than 10%, it should have outputted as yellow. And as you can maybe see in this graph, there's no yellow, which means the model closely mimics the values of the hand-derived segmentations, or at least the difference between end systolic volume and diastolic volume was consistent between the automatic and manual methodology. So that's pretty good news. Defining response to CRT as a decrease of 15% or greater of end systolic volume from before to after treatment, we defined 53 patients as responders and 19 patients as non-responders using the automated segments. So this is really close. This corresponds to green and red on the x-axis, so green responder, red non-responder. This suggests that one patient may have been right on the cusp of 15%, resulting in a different label between automated and manual. So all in all, I was pretty satisfied with the segmentation performance without having to load every single patient and time point into ITK Snap. But again, we could do that just to confirm that the absolute values are correct. So then, just to ease my worries, I plotted the left ventricle volumes over time. Um, so in the plots, time point is on the x-axis and volume is on the y. As you can see, there are no massive outliers, and most patients follow the inverted bell curve trend, in which the outlier points are the maxes and the center point is the min, or like near the center. We can therefore define the first time frame as end diastolic volume and the minimum volume time frame as end systolic volume for left ventricle. So lastly, the volume magnitudes do make sense, and therefore I can pretty much suggest we trust this data. We believe this data. My next sanity check, I was going to do the exact same thing, only now for left atrium. So recall that the left atrium fills with blood during systole while the left ventricle is draining blood. Then when the left ventricle is filling with blood during diastole, the left atrium is draining blood. Thus, we expect the graphs to have the opposite trend and be right side up bell curves, which is exactly what we see. Although not as clean, we still see the same general trends for all the patients. I inspected one of the outlier points, like the top patient over here, just to see what was going on over the time series. But the segmentation looked pretty good on ITK Snap, so I kept them in the final model, but we can always take them out if necessary. Also, because the left atrium is smaller, the volume magnitudes do make sense, and therefore I think that I pretty much believe this data without having to look at every single segmentation.
That
Okay.
also, can we pause for a second on that? That is the first time I've seen this data. It's really cool. So left is pre, right is post. Is the y-axis the same between left and right? So the shift in the data is an actual shift?
Correct.
Okay. Yeah, that's pretty impressive, right? How responders are going to be these people whose LAs have shrunk, right? Because
Yeah, what I could have done is like color code them responder, not responder, but MATLAB bugged out after 50 legend entries. So I couldn't even clear up. Yeah, I mean, I could have plotted them on two different or on four plots instead of two,
yeah,
but yeah, they're showing absolute differences.
no, that's pretty cool. Yeah.
All right, so before diving into the model results, I'll quickly review the learning models I tested in parallel. Um, I don't want to get too much into the weeds, but I think it's we have to understand some of the nuances between them and why some of them may perform differently. So first of all, they're all supervised learning techniques. So support vector machines, or SVMs, are about finding a hyperplane that separates two groups, which for us are the responders and the non-responders. They can handle different shapes in the data with kernels, and they're usually pretty stable, especially when the data set is a bit noisy or when we don't have tons of features. They're also less likely to overfit compared to the other models. That's important. Random forests are essentially a team of decision trees. Each tree looks at a different part of the data, and they all vote on the final result, essentially. Because of this randomness and teamwork, they're good at avoiding overfitting and can pick up on complex relationships in the data, especially when things aren't purely linear. And then we have the the logic gradient boosted trees, which take a different approach. Instead of training a bunch of trees in parallel, like the random forests, the gradient boosting trains them one after another. Each new tree tries to fix the mistake of the one before it. That usually means higher accuracy, especially for tricky cases, but the trade-off is that they can overfit if you don't fine-tune things like learning rate and tree depth. Also important. Okay, last slide, I promise, before the results, and I think this one's really important. So for the previous model, Ashish used SVM with bootstrapping since that data set was so small. Bootstrapping works by repeatedly resampling the original data set with replacement to create many training sets. Because of the overlap in the samples, each bootstrap model typically sees most of the data multiple times and can give a fairly optimistic view of how well the model performs. It's a bit like testing your model in data it's already familiar with. So we use the bootstrapping in 2023. But on the flip side, the k-fold cross-validation splits the data into k separate groups or folds and tests the model on each fold once while training on the rest. So I added a little graphic to explain that right here. Um, since each model is tested only on truly unseen data each time, this gives us a realistic estimate of the generalization performance. We also make sure the splits are stratified, meaning each fold has a balanced number of responders and non-responders, which is super important for an imbalanced data set like ours. So first I tried bootstrapping just to mimic what they did in 2023, but then when I got to the random forest and gradient boosted tree, the AUCs didn't look realistic, which you're about to see. So I did some research and hypothesized it was because of the duplicates of samples between training and testing. It wasn't as optimistic in the SVM because the SVM by nature is built linearly to prevent the overfitting. Therefore, I integrated the cross-validation approach for all the models just to have consistency and tested them in parallel. So yes, there's going to be a lot of data, but bear with me. I'm going to have a summary table at the end. Okay, so we have data. This is the original SVM model where we tested 6 different sets of data. Each set corresponds to the graph. Each set imports a different combinations of features from the new features table. So set 1, which is this one right here in the top left, is just the left ventricle strain metrics. So this is left ventricle global metrics, left ventricle regional metrics, just anything left ventricle. This was the one that was used in the model that was presented in the paper in 2023 by Ashish. The second set, which is right here, is left ventricle and clinical features. So these clinical features are usually what's available to the clinician before CRT. So this is what was presented before the paper in 2023, but this is integrated with the left ventricle. This graph right here in the top right is just the left atrium. So again, we're just doing left atrial global metrics. So these are the ones I computed today or for this project. And in the bottom, set 4 is left atrium with clinical. The middle right here is left atrium with left ventricle without any clinical. And then this last one right here is left atrium, left ventricle, and clinical. So essentially all the metrics. So as you can see, the AUC is decent for all, but the best uses all the features in the bottom right with this AUC of 0.99. Again, still kind of hesitant with the bootstrapping results. I couldn't replicate exactly the same results as Ashish because I didn't use the same seed, and I think some of my parameters for the bootstrapping were a bit different. I think he got a 0.87, but I got a 0.88 AUC for the left ventricle. But ultimately, this is showing us the trends with what happens when we add more variables, and just using the left atrium by itself isn't sufficient for this use case and this model. Okay, moving on to the next result. So here, same results, bootstrapping results with the SVM, but now I've created scatter plots in which the y-axis is the patient's change in end systolic volume. So at a cutoff of minus 15%, which corresponds to this horizontal line, patients are defined as responders below this line and are represented by blue plus signs. And then patients above this line are true non-responders and are represented by red circles. The x-axis is the score assigned to each patient. In MATLAB, I defined the score as the Youden threshold, which is the score that maximizes the difference between true positive and false positive rates. So this differs from Ashish's methodology for assigning the threshold score. I think he used a threshold that maximized the geometric mean of true negative and true positive. The reason why I did this Uden threshold, I didn't know what it was. ChatGPT helped me, but I could do it consistently between all my learning models. So I wanted to do the Uden for all the SVM, the random forest, and the gradient boost. So that's why I just kept it consistent. And then, so patients left of this vertical line were predicted not to respond to CRT, while patients right of the line were predicted to respond well. And then I've also added patient counts for each of the quadrants. So if you had a perfect situation and it predicted really well, all the blues would be in this corner and all the reds would be in this corner. And then you would have none in the false positive, true, false positive, false negative boxes. And then again, each scatter plot represents the 6 sets that I presented before. All right, moving on. Random forest. Hold on. Just to show you all the data. So here you can see the bootstrapping results for the random forest model. As you can observe, these AUCs are quite high. This suggests that the model can almost perfectly predict response to CRT. This may hint that the model is overfitting. We don't know that for sure yet, but you can see here that we're getting AUCs of 1.00, which is pretty spectacular if that actually is true. And then here are the associated scatter plots, which again show a very good prediction for all sets of metrics. And then moving forward to the gradient boosted, we got AUCs of 1 for everything. So I knew this was a little too good to be true, at least I thought, since I got a AUC of 1 across all metric sets. And here you can see the perfect case scenario for the associated scatter plots, like I said before, with all the responders predicted to be in this quadrant and all the non-responders predicted to be in this quadrant. But again, a little dubious of the results. And that's why I had to do some research figuring out what was causing this. What can we do to not be a little too optimistic with the model? So that's why we went to the five-fold cross-validation results. So I did everything exactly the same, but now instead of doing the bootstrapping with replacement, I did the five-fold cross-validation. And just to summarize, or just to repeat myself from before, now we're not seeing the same data in the testing and training, which can hopefully provide more reasonable AUCs that we trust. So here are the results for the five-fold cross-validation for the SVM. Again, this is the original model used in the paper. And if we look at this, the left ventricle, it dropped from 0.88 to 0.71. And then if you add clinical, you increase it. If you add atrial, you increase it even more. So about the same trends that we've been seeing before. Here are the associated scatter plots, which with again much more reasonable results. And then now we've entered pretty new territory, which is now we're using the new random forest technique with the cross-validation approach for all 6 combination of metrics. To note, the left atrium by itself is not performing well. It's actually worse than chance.
Yeah, you just have to do the opposite of what it tells you to do.
Yeah, exactly. Yeah, exactly. But the good news is that it did improve the results confounded or combined with the left ventricle and the clinical, which is pretty decent. But in this one specifically, it didn't do too much different from just the left ventricle and clinical. So in this model specifically, left atrium, the extra work for incorporating those metrics isn't absolutely necessary in this model.
Right.
Here are the associated scatter plots. And then now the very last 2 slides for results. The last iteration results, I'm showing the gradient boosted tree model with the five-fold cross validation. So this is actually our highest AUC value with the cross validation results here. I know this also says 0.8, but I'm about to show you this one's actually a tiny bit higher. And then here are the associated scatter plots. So here we summarize everything. At the top, you can see the AUC results for all combination of sets, models, and validations. To conclude these findings, bootstrapping may have caused some overfitting, especially for the random forest and the boosted gradient models, which is why we tested the fivefold gradient or cross-validation in parallel. These results may have been more realistic for this retrospective study, even though left ventricle plus clinical results performed quite well when appended with the left atrial strain, this slightly improved the performance. Although when adding left atrial strain metrics to left ventricle strain metrics alone, this improved the results when bootstrapping, this worsened the results when cross-validating. And then the logic gradient boosted tree model almost always performed best, although it most likely was overfit when using the bootstrapping approach. And then all that said, I bolded the highest AUC on the cross-validation side. In my opinion, again, I haven't looked at these in too much detail or done any sort of checking for overfitting or anything. But all that said, my opinion is that the logical gradient boosted tree model with all the metrics should be used as a predictor model for CRT response. And again, I didn't do a PCA to see what variables were really driving it, but that's something you could do to really isolate which variables you were using and which columns in the features table you were importing. So to end, some possible next steps could be to do a much larger cohort so we don't run into the issue of having to bootstrap or cross-validate. We could do a traditional 40-40-20 split for train test validate. And then these other directions, they were mostly from my conversations with you, Dr. McVeigh, but we could incorporate additional metrics to the model, such as the myocardium. I also acquired this data after smoothing the 40CT data. If we're able to, a next step could be trying to do this from the raw data, if we have a cool model that can do that. And then lastly, we could use higher resolution lead placement meshes to better predict responses and placement of the leads. Although I didn't focus on this for this project, this was discussed in the original paper and could be another future direction. So I've also included the AUC of the last model, which I thought was the best here. But otherwise, that is it. Thank you, everyone, for listening. I can take any questions.
Great. That was a tour de force. That's a lot to take in all in one go. Do you think, but I mean, part of the problem obviously is when you're trying to do the validation model with that number of patients, right? With where you only had 82, right? And so your cross validation is a little bit small, and therefore you start to get these strange looking curves, right? Because they, as individual or little groups of patients move this way or that on your scattergram, the curve changes a lot. Um, do you think if you had, say, 400 patients or whatever we have 300 or something patients, that curve is going to start to smooth out and give us a more.
Yeah, I think to echo what you just said, every time I ran it, it was a couple of percentage points up and down based on the random seed. So I think the results will be more consistent and the smooth will get, or the curve will get smoother if we have
Yeah.
more patients. Yeah.
Oh. And then from the clinical data, was there anything in the clinical data that would map directly to a correlation with the atrial data? Do you know?
Yes. Let me look at I have the Excel sheet up with the features table. So again, even though I said we use all the clinical features, I only use the columns that Ashish used. So even though we have like one columns, only some of them are used. So I don't know for sure if this was incorporated, but there's actually no, maybe there's not. There's RV diameter. It's not, I thought it was LA
Oh,
diameter
okay.
from
Yeah.
Echo.
Okay.
CAPSI, max TRPG, hemoglobin, QRC, so maybe QRC
Yeah.
should have some left atrium. Sex, ICM. What's ICM? ICM,
What
I don't
is
know what
it? Yeah, I've forgotten.
I don't know what ICM is. MI, it's binary, so I guess if they had it,
Yeah, it's
if
had a
they
previous
had it,
one. Okay.
cabbage score and then perm aphid. So those are all the metrics. But again, I have to look in my MATLAB script to see which columns were imported, but I don't know if any of those suggest direct
Yeah.
correlation to
So
training.
AFib might, and also TAPSI might correlate
Okay.
a little bit with left atrial function. Okay, cool.